So today we're going to do the practice exam, and this is going to feel very similar to the actual exam that you're going to see in a little bit. So for instance, this has 25 questions. The actual exam has 26 questions. They're both multiple choice. That's kind of the point of the practice exam, is to help you to take what you've learned and to put it into this format. The practice exam has 2 attempts. Of course, your regular exam just has 1 attempt. My recommendation, and hopefully you've already done this, is to take this practice exam, as I call it, blind. That is, just like you were taking the regular exam. You sit down with just the periodic table, and you could use the equation sheet, although you won't need it, that I published on the front page of the course website, and some scratch paper and a calculator, and just do it. And if you take it blind like that, what I find, generally speaking, it's not perfect, but generally speaking, the score that you get there is a pretty good reflection of what you can expect to get on the test. Of course, I don't want you to stop there. I want you to notice what you missed and why. So after you take it the first time, check what you missed, study it up, and then I do recommend that you either watch the video that I already published of me doing the practice exam, or come here, do it with me. So you can kind of see the approach that I use when I'm looking at a problem, my thought process when I see it, and how I engage with that problem. Make sure you're getting the ones that you got right for the right reasons, and make sure that you're understanding the ones you got wrong and why you got them wrong. So that's what we're doing today. We probably will not take up our whole 2 hours. Hopefully it doesn't take me a whole 2 hours to do this practice exam. And then I will let you go, so I'm giving you some time to take your actual test. So, all right, any questions on that before we get started? All right, well, if there's no questions, then we can just jump in here. So question number 1, density would be correctly classified as what kind of property? We have intensive, extensive, chemical, or like a state of matter. So if we remember, intensive means it doesn't depend on the amount. Extensive means it does depend on amount. Chemical means that you would have to change the identity to measure it. And state of matter means like a solid, a liquid, or a gas. So which of those sounds like it applies to density? It's intensive, right? Density is the ratio of the mass to the volume. Either one of those, mass or volume, alone would be extensive, right? Because the more you have, the more it weighs. But that ratio, as Nicole noted, is intensive. So water has a density of 1 gram per milliliter. If you have a whole bunch of it, it still weighs more, but it also has more volume, and the number of grams divided by the number of milliliters should still be about 1. Excellent. Good job. Oh yeah, Erica, go ahead. Okay, so Erica says density always a constant. And for a particular substance at a particular temperature, it will be constant, right? So for pure water at, I think, 25 degrees Celsius, it's 1 gram per milliliter. But it actually is temperature dependent. You'll see some small changes as you go down towards freezing or as you go up towards boiling point. And of course, the density of one substance is different from a density of another substance. And so we don't think of it as constant as in like all density is always constant, but for a specific substance at a specific temperature, then that would be constant, yes. Does that make sense? So the question is, what about specific elements? They will have, again, each element will have its own specific density, which is unique to that element at a specific temperature. The density does not vary significantly. So for instance, for water, you can expect it to be about 1 gram per milliliter across the whole range. It might range from like 0.99 to 1.01 or something, but it's a very tiny variation. But it is specific enough to an element that, for instance, you could use it to identify an element. I believe that you've got that in one of your labs. Your 1115 lab has this question about a guy who somebody's trying to sell him this fancy gold coin at a shop somewhere, and the scientist pulls out his volumetric flask and his balance to check the density of it, because he knows that if it's gold, it'll have a certain density. And if the density is different, then it's not really gold, right? So zinc has a different density than gold does, and gold would have a different density than copper does. And so if you don't know the identity of a metal, but you can find its density, you can make a guess as to what it could be. You could certainly eliminate certain other options. Does that sound like a familiar problem from your 1115, from your chem lab? Not yet, no. Okay, well, you'll see it, I hope, because it's kind of a fun one. But yeah, it's unique to different elements. In fact, I could just pull this up here, densities of elements. I just Google image searched density of elements, and you can kind of see here, ignore the price here. Gold here has a density of 19.28 grams per centimeter cubed, which is the same as a milliliter. So remember, water is 1 gram per milliliter. Your gold is 19 grams per milliliter. If somebody took lead and then covered it in gold flake, so it looked like gold, it would not have the same density. And you could see that when you measured the mass and the volume and then took the ratio of that. Interesting. This is showing price per kilogram, but I mean, californium, berkelium are synthetically made, and you're not going to get a kilogram. You're going to get like an atom or two and then see that it splits. So that price is the cost of the program that's making those elements. It's kind of funny. Okay, you will not get a chart, Erica. You won't need a chart. If I ask you about density, then I will give you the numbers to calculate it, because it's just an easy dimensional analysis problem where I give you grams and milliliters. I think for the lab where you do that comparison, you'll probably have to look it up. Yeah. Okay, so question number 2. Which of the following samples will, by definition, have a constant composition? Multiple answers may be selected. I don't do that on the actual exam. I think it's all just multiple choice, but careful. Perfect. Erica says water and oxygen. Good. Water is a compound, but compounds still have a constant composition. This is another way of saying which of the following samples is a pure substance, because pure substances by definition have a constant composition. Or which of these following samples is not a mixture, because mixtures by definition do not have a constant composition. So water and oxygen are pure substances, compounds and elements, whereas these two would be mixtures. Does that make sense? Excellent. Okay, precision refers to what? Perfect, Sarah. Precision refers to how close a measured number is to other measured numbers. If you are very precise, then all of your numbers are very close to one another. So you're getting repeatable results, and the digits agree with each other. If I asked you about accuracy, if I said accuracy refers to what, then which of these would be the correct answer? That's right, the true value is for accuracy. Good. Excellent. Okay. Now this is a kind of like the question that we were just looking at, describing density. And you can see what I mean when I say I'm not going to give you a chart, but it's dimensional analysis. You've got all of the information you need. So for question 4, an object has a mass of 40.1 grams and occupies a volume of 9.51 milliliters. The density of this object is what? And Sarah's got the answer here, but I just want you to note, I didn't give you a formula for density, and I never will. Because there is a formula for density, but nobody needs to memorize a formula. What a waste of your brain space, right? You can look at this and say, oh, the units are grams divided by milliliters. I have grams, I have milliliters. I think I can put that together. You guys can put it together. I expect that you can. So honestly, yeah, it's 40.1 grams divided by 9.51 milliliters. That is the analyzing the dimensions, analyzing the units, putting them where you need. And you should never have to worry about memorizing a formula. It's just not worth your brain space, right? Brain space is precious. There's other things to remember, right? Like all the lyrics to the latest song that just came out that you really like, right? So 40.1 divided by 9.51 gives you 4.22 grams per milliliter. And of course, there's a lot more digits here, but I rounded it to 3 because they only gave me 3 here and here. All right, does that make sense? You with me? Okay. All right, next we're going to perform the following conversion. We're going to go from 5.07 meters per second to how many kilometers per hour. So this is also a dimensional analysis one, but this is a little bit more complicated. So we're going to put it over here so we can see what we're doing. Now, we've got our 3-step method, right? Step 1 is to say, what are they looking for? What are our target units? Kilometers divided by hours. So these are our target units, and I'm showing it this way instead of this way, even though they mean the same thing. But if I put it this way, then it's a little bit clearer that that's my target for my dimensional analysis. Clearer to me, at least. Okay, step 2, we're going to list everything else they give us that might be helpful for this. What do you see? What are we given? Yeah, we have 5.07 meters per 1 second. And again, they say meters / seconds, but I'm gonna very specifically put it over. Actually, I'm not. I'm gonna do it this way. I'm gonna say 5.07 meters is equal to 1 second. Okay, what else did they give me? Or what else do I need to know for this? We need to know meters to kilometers. Okay. What is the conversion for that? Will I give it to you? Is it on the equation sheet? All right, Sarah says we've got 1,000 meters is equal to 1 kilometer. And Erica notes, for the sake of all of us here, that I will absolutely not give you that. You have to know that to put that down, because that's a metric system. Okay, what else might we need to know to answer this question? Good. 60 seconds is equal to 1 minute. Perfect. Yes, what else? 60 minutes in 1 hour. This is common knowledge that I expect you to know as well. Okay, I think that's everything we need. So now, step 3, we're going to set this up. And where shall we start? Okay, 5.07 meters per second. And remember, there's more than one place you could start, but this is perfectly appropriate to start right there. That's totally fine. Okay, here we go. What do we do next? All right, good. Sarah wants to do meters to kilometers. And again, there's not like a right or a wrong one of these to start with. You can convert away from the meters or away from the seconds, but it's not a problem. So when I do meters to kilometers, what goes on top and what goes on bottom? Kilometers needs to go on top. Okay. 1 kilometer in every 1,000 meters, using this second one that was given right there. Okay. Excellent. So I've used this guy and I've used this guy. All right, what should I do next? Seconds to minutes, Sarah says. Okay, we can do that. And what am I going to put on top? We're going to put seconds on top so that they will cancel. So 60 seconds in 1 minute. Good. Just to kind of verify here, my meters canceled here. And here I have seconds divided by seconds. They don't have to be next to one another, just so long as one's on top, one's on the bottom. Good. Now I have got this as kilometers per minute. What do I need to do next? Minutes to hours. What goes on top? 60 minutes. Perfect, Tiba. And 1 hour. Okay, and now I'm paying attention. My minutes cancel. What do I do next? Perfect. Sarah says plug. That means I'm done, and I need recognize I'm done because I have kilometers on top and hours on the bottom, exactly as our target units would indicate. So we stop converting, and now we just plug it in. Okay, so 5.07. I'm going to divide that by 1,000, multiply that by 60, and multiply that by 60 again. And that gives me 18.252 or 18.3 kilometers per hour. How do you guys feel about that? Okay, excellent. Remember, the nice thing about multiple choice is that the correct answer is right in front of you. But be careful, because multiple choice means that every common wrong answer that you could get is also in front of you, right? So if you did this upside down, if you just answered in hours per kilometer instead, because you weren't paying super close attention, then that would give you 0.054, right? And that might, oh, that's not on there. Right, but if you forgot one of your 60 minutes per hours, right, or if you forgot to do the 1,000 meters per kilometer, right, there are a lot of other things you could do that would give you some of these other numbers, so be careful. Okay, dosing. Oh, are you surprised there's a dosing problem? There should be no surprises that there's a dosing problem here. No surprises that there are 2 dosing problems here, 6 and 7. Okay. All right. No, I'm a little surprised there's not 3 dosing problems here. Okay. Here we go. We can do this again. So, step 1, a little line here. Step 1, identify the target units. So I'm going to read this here. If a 130-pound woman takes 2 to 325 milligram tablets of acetaminophen, what is the dosage she receives in grams per kilogram of body weight? I'm pretty sure you had a question just like this on the homework. Okay, so yeah, Sarah's right. We need grams per kilogram, and specifically, we need grams of acetaminophen divided by kilograms of body weight, right? I'm going to be specific about what the grams is referring to and what the kilograms is referring to, because now we're going to want to pay attention to both the measurement units of grams and kilograms and the identity units of like which of these is referring to acetaminophen, which of these is referring to body weight. Because if I have grams of acetaminophen, I can translate that to kilograms of acetaminophen, and that would be wrong, but it might be misleading. I might think that's what I'm supposed to do because there's kilograms there. Does that make sense? Be very careful. Okay. Next, what are we given here to help us solve for grams per kilogram? All right, we have a 130-pound woman. Okay. Specifically, that's my body. Okay. I mean, not my body personally, but that's the body in the problem. Okay. And what else do we have? We have 2 tablets And each tablet, one tablet, is equal to 325 milligrams, right? I mean, they really kind of shortened that. She takes 2 325 milligram tablets, but that's essentially what we're saying. 2 tablets, each one is 325 milligrams. It'll help to kind of pick that apart. Okay, what else are we gonna need? We're gonna need pounds to kilograms in some way or somehow. Now, if this was an exam, I have to give that to you. I should have given it to you because it's the practice exam, but I didn't. But let's say I gave you 1 pound is equal to 454 grams, then that would be sufficient to get you there, okay? And we also need, as Nicole and Sarah noted, we need milligrams to grams. What's the ratio of milligrams to grams? 1,000 milligrams is equal to 1 gram. Perfect. And okay, hang on a second. 2 tablets. This is my acetaminophen. This is acetaminophen. Acetaminophen. Just want to be specific on our identity as well as our measurement units. And then these 2 conversions are universal. That is 1 pound of anything, including acetaminophen, is going to be 454 grams of acetaminophen. And 1,000 milligrams of anything, including my body, is going to equal 1 gram of my body. So I need to make sure I could use these for anything, but make sure that I'm watching my identity when I do it. Okay, I think that's all we need for step 3, putting it together. Where shall I start? 130 pounds women's. Okay, perfect. 130 pound body. Okay. What shall I do next? All right. Sarah's like, I'm not going to mess with your garbage units, Mary. I'm going to use what I know, which is that 1 kilogram is 2.2 pounds. You can totally do that. If you know it, just use it. It is easier than the one that I gave you. That's totally fine. 1 kilogram is 2.2 pounds. Just as long as you don't mix it up, because like I told you, like it took me 2 decades to find a way to make me not say that 2.2 kilograms is a pound and be completely backwards. Oh, good. Okay, so Erica says, don't we need kilograms and not grams? You mean for the body mass? Yes, you do. But because I'm rude, I gave you the pound to gram conversion. So you would have had to go from pounds to grams. And then because, of course, you know metric conversions, that should be trivial to go from grams to kilograms. So that's why I said I was rude. I gave you this conversion that was going to make you take an extra step and use the 1,000 grams is equal to kilogram. And then Sarah said, I'm going to use this other conversion factor because I don't want to waste my time with that. So on an exam, if you have these tools that could help you find the answer, but instead Sarah said, I'm just going to use that 1 kilogram is 2.2 pounds. Does that make sense? It'll give you the same answer. All right, so in terms of converting from my pounds of body to kilograms of body, whether I go from pounds to grams or grams to kilograms, or whether I go from pounds to kilograms using this other conversion, doesn't matter. Okay, so now we have solved for kilograms of body weight. Okay, so what shall we do next? Oh, look at you, Sarah, you're gonna confuse everybody. Not really. Okay, Sarah also says, look, I'm not gonna do dimensional analysis with this guy, although you could. I'm just gonna take 2 times 325 and convert that before I plug it into anything and say, look, she's getting a 650 milligram dose. I'm just not gonna waste my time with dimensional analysis. I'm just gonna convert that before I do anything else. You're totally fine. But I just want you to know when Sarah says, hey, look, it's 650 milligrams, this is where she's getting it from, right? So you can set up the dimensional analysis and say, you can set up the dimensional analysis and say, I've got 2 tablets, acetaminophen, and then you can say, all right, and then we've got 325 milligrams acetaminophen in every 1 tablet acetaminophen. So this is the official dimensional analysis way to do it. But sometimes when you're learning, I encourage you to practice it just because it's good form. But when you're here, if you know how to do it, you feel really confident. There's nothing wrong. Nothing wrong with doing that shortcut here. Okay. So anyway, so this is the dimensional analysis way to do what she just did right there. All right. But she did it there already. I'll change to a different color. And then Sarah says, now I'm going to do my grams to milligram conversion. So I'm going to say that there's 1 gram of acetaminophen in every 1,000 milligrams of acetaminophen. And if I do that, then my milligrams of acetaminophen cancel, and I'm left with grams of acetaminophen. Okay. That's fine. This is what makes sense to you guys. What should we do next? All right. So what Sarah did, hopefully you guys can see, and this is fine. It's totally fine. It's what makes sense to her, and it might be what makes sense to you as well. She just calculated each of these individually. So 130 divided by 2.2, she says we've got a 59.09 kilogram, 59.09 kilograms that we calculated first. And then 650 divided by 1,000. So I have a 0.65 gram of acetaminophen. And now she just says, hey, I want the grams on top. So now I'm going to assemble it thusly. 0.65 grams acetaminophen divided by 59.09 kilograms body. And divide one by the other to get my answer. Now this is a little bit more roundabout than I would have done it, but it is not wrong. Okay, so I have 0.011 grams per kilogram right there. Does this make sense to you guys? It might be that this makes sense to Sarah, but not necessarily to everybody else. So we can do I really like doing the whole dimensional analysis, like all one long line. I feel very accomplished at the end of a 4 or 5 step conversion, but this is okay too. This is okay too. This is one advantage to this is that we have kept apart. I want you to notice that we did all of the body conversions in one place and all of the acetaminophen conversions in one place. So we didn't end up accidentally like crossing our identity lines inappropriately, and that happens. Okay, all right, so there is that one. All right, let's look at question 7. Got more to do here. I'm gonna zoom out, hold down. Okay. All right, for question 7, we're given the recommended adult dose of penicillin is 0.01 grams per kilogram. We want to know how many 150 milligram tablets a 32-pound child would have to take in order to receive the same dosage. Okay, so number 1, what are our target units? Tablets, the number of tablets of penicillin. Okay. It's very confusing. It almost, because you're receiving the same dosage, it almost makes you think you're looking for grams per kilograms, but no, the question is how many tablets? So be very careful with that. Hopefully this 3-step method has helped you guys kind of sort the numbers that are in these word problems. Okay, next, what have they given us? We have a 32-pound child. Okay, or a 32-pound, child, that's your body. Okay. We have a dosage of 0.01, and they don't say it specifically, but that is grams of penicillin in every 1 kilogram of body mass, right? Good. And they tell us that 1 tablet of penicillin contains 150 milligrams of penicillin. Okay. Excellent. That's all the stuff that they told us specifically. What else are we going to need to make this work? We're going to need milligrams to grams because we've got milligrams of penicillin here and we need grams of penicillin here. Okay, so what conversion factor do you want to use here? (1,000 milligrams equals 1 gram. You guys like that one? That's great. And then Erica notes we're going to want the 2.2 pounds is equal to 1 kilogram. Again, I'll give you either that or this one here on the exam. All right, and of course these ones apply to anything. So we're going to want to make sure that we're just following our identity units properly. All right, so step 3, let's put this together. Where shall we start? What makes sense to you? Sarah says she wants to start with 32 pounds. And that's my body. Okay. Now what? All right. 1 kilogram of anything is equal to 2.2 pounds of that thing. And here we're talking about the pounds of the body, so that's got to be kilograms of the body. Good. Excellent. Now what? David notes that he started with the adult dose. He started with the 0.01 grams per kilogram at the beginning, which is also totally fine. Sarah is going to do 2 different conversions again and put it together like she did in the first place. But I'm going to keep going just like David might have started with this one. He would put 0.01 grams of penicillin in every 1 kilogram of body. This is a convenient place to put that because, as we noticed, here are my pounds of body cancel. And here, if this is my adult dose, my kilograms of body will cancel. So it's convenient to continue from there. But you could have easily started from here, as David notes, and then moved away from that using these mass conversions. Again, so long as you end up with the right units in the right place, then you're totally fine. There's not like a right or a wrong way to do it. Okay. So we've used the 32-pound child, we've used the adult dose. Right now we're at the number of grams of penicillin and we still need to get to tablets of penicillin. So what are we going to do? Grams to milligrams. Perfect. Excellent. So we're going to say, what's going to go on top? What's going to go on the bottom? Milligrams on top. Good. So 1,000 milligrams of anything, in this case penicillin, and every 1 gram of anything, of course, in this case penicillin. So now my grams of penicillin cancels. And what next? Oh my goodness, you're correct. Should be a little M there. No, oh geez. Should be milligrams of penicillin there. Oh, just delete that. Thank you for catching that, Sarah. Okay, so now we've got milligrams of penicillin on top. We still need to get to tablets. What shall we do? Perfect. Nicole says we need 1 tablet of penicillin over 150 milligrams. Penicillin. And we want to put the milligrams of penicillin on the bottom because then milligrams of penicillin divided by milligrams of penicillin will cancel, and I'm left with tablets of penicillin, which is exactly what I wanted, so I can stop the insanity and just plug it in. So 32 divided by 2.2, multiply that by 0.01, multiply that by 1,000, and then divide that by 150, and I get 0.969696. That's not here. How many tablets should I give them? 1 tablet. It's very close to 1. Good enough. Does that make sense? Hopefully not too tricky. All right, let's see here. The metric system used to measure volume is the liter. Perfect. Let's see. If I had said the metric unit used to measure mass, what would the answer have been? Grams. Perfect. And if I had said the metric unit used to measure distance is what would the answer have been? Meter. Okay, you guys got this. Excellent. Okay, express this number in scientific notation. Good. Okay, so if your decimal point is here, you move it to the left 1, 2, 3, 4, 5, 6. You're going to get 1.45 times 10 to the 6, just as Sarah noted. That's how she got that answer. Any questions on that one? Okay. What about, ooh, this one is so rude. Which measurement represents the largest quantity? And of course, they were all given in like different units. So you have to convert these to one that's so that you're comparing apples to apples. Note on this one, I think you had a question like this on the test. I mean, on your homework. Does this sound familiar? I think there's one like that on homework. 4730 nanograms. Oops. 4.73 times 10 raised to the 4th grams. 4.73 times 10 raised to the 3rd micrograms. 4.73 times 10 raised to the negative 6th kilograms. And 47.3 milligrams. Negative 4. Good eye. Thank you, David. All right. Okay, so we need to convert these all to the same thing so we can compare them. So I'm going to convert them away from nano or micro or kilo or whatever, and we're just going to convert them all to grams to make our lives just a little bit easier. So to convert this to grams, I just have to remember that nano means times 10 to the negative 9th. So this is like saying 4730 times 10 raised to the negative 9th grams. Makes an easy conversion. This one's already in grams, so 4.73 times 10 raised to the negative 4th grams. 4.73 times 10 raised to the negative 3rd. And then micro means times 10 to the negative 6. 6 grams. That's basically what that's saying. And then for the kilograms, it's 4.73 times 10 raised to the negative 6th, and then kilo means times 10 raised to the 3rd. And then 47.3 milli means times 10 raised to the negative 3rd grams. Whoops, did not mean to do that. I don't even know what I did. But I like moved the whole thing up somehow. Let me put that back down. Okay. Put a negative. Oh, I did put a negative in the micro. Why did I do that? That's weird. Okay. See, these are the kind of silly mistakes that would make me get this problem wrong. Because I'm missing negatives. Okay. Does everybody understand what I did there? Okay, I used the conversion factors. Let me pull these up here from my lecture notes that I recommended that you guys memorize. So on the math section, math and chemistry lecture number 1, numbers. Bring this over here. Units, here we go, this one right here. And I said micro is times 10 to the negative 6th, and milli is times 10 to the negative 3rd, and kilo is times 10 to the 3rd. Like if you just memorize this side of the table here, right? Then you can always get the right conversion factor, because you can remember that 1 gram is equal to 1 gram. And then you remember that milli means times 10 to the negative 3rd. So you can just insert that times 10 to the negative 3rd. And so then you have the correct conversion factor of a milligram is 1 times 10 to the negative 3rd gram. Right, so that's what I use. And I know that you might not love that. You might say, look, I'd much rather say that there's 1,000 milligrams in 1 gram. And that's fine too, right? If you're like, whoa, I would rather use this, then what you would need to do is just do that conversion, right? And say, for instance, 4730 nanograms. Sorry, I'm going to do this one right here, 47.3 milligrams. And then you're going to do a little dimensional analysis and say, for instance, okay, well, there's 1 gram has 1,000 milligrams, if you'd rather use that. And then plug that in. You'll get the same answer as I did here. 47.3 divided by 1,000 is going to get me 0.0473, which is what's going to happen when I take this negative 3 and move it back, walk it back there. Okay. So there's more than one way to do this. This is just one way. If you don't love it, it's okay. There's other methods. All right. So the next question Erica says is like, what do you do when I'm what with the multiple exponents, right? Like you kind of know what to do with these exponents because you know how to convert from scientific to regular. But what if we're doing this? And you could do it with your calculator because you're given a calculator, but there is actually a rule of thumb for exponents. And that is if you're multiplying exponents, then you just add them together. But if you divide exponents, then you subtract them. So here, if you multiply exponents, you're just going to add them together. 10 to the 3rd times 10 to the negative 6th. 3 minus 6 gives you negative 3. And so that adds up to 4.73 times 10 raised to the negative 3rd. If you don't want to remember that, it's okay. You can still plug that in to the calculator and say, I have 4.73 times 1 times 10 to the 3rd is how I have to do it. Oh, geez. Hang on a second. I hate Windows calculator. I need to like download a better scientific calculator. But okay, so the way that this one has to do it, 4.73 times 1, oh, there it is, 1 times 10 to the 3rd. Multiply that by 1 times 10 to the negative 6th equals Okay, what happened there? Something went horribly wrong. Are you seeing what? Oh my gosh. Okay, let's try this again, but this time I'm going to multiply instead of add that to 1,000. I would have missed this problem on the exam because I am not paying close enough attention. 4.73 multiplied by 1 times 10 to the third multiplied by 1 times 10 to the negative 6th, close those parentheses, equals, there we go, 4.73 times 10 to the negative third. Is that what we got? That's what we got. Okay, Sarah notes that you can only use this trick of adding or subtracting exponents if they're both the same base, but they'll always be base 10 in this class. We will never use any other base. So you don't have to worry about that. But okay, so all right. Aha. Okay, so the first thing we did was we converted everything to grams so that we're comparing apples to apples. But now we don't have everything in the same exponent, so now we need to convert things to the same exponents. And we're going to start by simplifying these two that have more than one exponent. Okay, we're just going to add them. And we did this one, 4.73 times 10 raised to the negative 3, because positive 3 plus negative 6 is negative 3. What about this one? What's this one's going to be? 4.73 times 10 to the negative 3 again, because here now I have a negative 6 here, plus a 3 still gives me negative 3. So these ones are the same, which is good, because that tells us they can't be the right answer, because I'm looking for the one that is the largest. I can't have two that are the largest. So they will not be the right answer. All right, let's compare that to the other ones that we've got here. We still aren't comparing perfect apples to apples because we don't all have the same power of 10, right? These are both the same power of 10. This one is also, which one of these is larger? This 47.3 milligrams or these two that were the same? The 47.3 milligrams, because when we convert it, perfect, Sarah, because when we convert it to negative 3, we're comparing 4.73 times 10 to the negative third versus 47.3 times 10 to the negative third. Since the times 10 to the value is the same, but the 47 value is larger, then this one is bigger. So currently, when we compare all three of these, this one is the biggest. So now we need to compare this one versus these two up here. And so we want to have the same exponent number. So to move this from, we could either move everything to 10 to the negative 3, or we could just convert it just to straight grams, which maybe you have wanted to do that since the beginning because you're like, I don't like these prefixes. They look terrible to me. If we just converted these to straight grams, we're just going to get rid of the scientific notation. And we're going to say, look, I like normal notation, right? So I'm going to move this over because this is negative. I'm going to make this a smaller and a smaller value. I'm going to move it over by 9 times. So this is going to be 0.1, 2, 3, 4, 5, 6, 7, 8, 9 grams is what that is saying. Does that make sense to you guys? Okay, and I do this here. I have to move that decimal point to the left 4 times. So 0.1234 times 7.3 grams for this guy. Here I need to move that over to the left 3 times, 0.123 grams. Okay, and then this one, again, I have to move it to the left 3 times. So I'm gonna have 10 and 473 grams. And that's a lot easier to see. Now that I got everything in grams and I got rid of all of this, the scientific notation, that should be clearer that the 47.3 milligram is the largest one. Does that make sense? Okay, again, there's a couple ways of doing this one. You could have just, from this point, plugged it into dimensional analysis as I was showing you and converted it straight to grams on your calculator. Just been like, I don't want to mess with this, but I do want you guys to have kind of an understanding of what these exponents mean. Okay. All right, a couple more dimensional analysis. Oh, yep, here's another one. Almost looks like a dosing problem. We're not done with dimensional analysis yet. Okay. If gasoline sells for 95.4 cents per liter, what is its cost on a per gallon basis? Given 1 liter is 1.06 quarts and there are 4 quarts in a gallon. Okay, we can do this. No tricks. Step 1. What are we looking for? Dollars per gallon. Good. So step 1, we want dollars per gallon of gas. Okay. Excellent. Step 2, what did they give us? Got 95.4 cents per liter. Okay, that sounds cheap. Is that cheap? I don't know. I don't know the metric system. What else did they give us? One liter. Whoops. 1 liter is equal to 1.06 quarts, and 1 gallon is equal to 4 quarts. Okay. Anything else we're going to need for this? Dollars to cents. Okay, I'm not going to give it to you. I hope you guys know this. Some things you just ought to know. Yeah, 100 cents is equal to $1. It feels weird to put the dollar sign after the 1, but I'm going to do it anyways because that follows the format that we use for all of our units here. Okay, that should help you remember. I mean, there's 100 years in a century, 100 cents in a dollar. Hopefully that helps you remember the centi for centimeter or centiliter. That metric prefix is that there's 100 cents, 100 centimeters in a meter. Okay, I think we have everything we need to set this up. So where should we start? Where do you want to start? All right, Nicole wants to start with 95.4 cents in every 1 liter of gas. Great place to start. What shall we do next? 1 liter over 1.06 quarts gasoline. Good. Note, I'm not being as stickler on the identity units here, just because I don't think that there's any worry of you getting confused between liters of gasoline and cents of money. But it's easy if you've got milligrams and grams, right? Or kilograms and grams of like body and drugs. Okay, all right, so liters cancels. Now we've got cents per quart. What shall we do next? All right. Nicole says 4 quarts in a gallon. Great idea. quarts cancel. Now we have cents per gallon. What do we do next? $1 over 100 cents. And now our cents cancels. And we get dollars over gallons. Alexander says, I didn't do it in this order. Does it matter? And the answer is, it doesn't matter. So long as you get dollars on top and gallons on the bottom and everything is canceled out appropriately, it's totally fine. This is starting, as I mentioned, starting at the beginning with this thing that you're given. But often I'll start at the end. I might have started with dollars over cents to get dollars on top, or I might have started with quarts over gallons to get gallons on the bottom, since I knew that's what I wanted. You can start anywhere you want, so long as you're watching your units really carefully and you make sure that you get the right units in the right places at the end, then you've done it right. You'll get the right answer. Totally fine. Yeah. You just say, hey, I've got dollars over gallons. That's exactly what I wanted. There's nothing extra. Then I know I'm done and I can just plug it in. So 95.4 cents per liter divided by 1.06 quarts multiplied by 4 quarts in a gallon divided by 100 cents. And that gives me a price of 3.6, which corresponds to $3.60. Is that a good price? Probably not today anymore. There's been times when that's a good price. Not a good price today. This is one of the reasons I tell people we should totally adopt the metric system, because gas is cheaper, right? Who doesn't want to pay 95 cents per liter instead of $3.60 per gallon? Isn't that cheaper? Not cheaper? Nope, David says it's not cheaper. We just calculated those are the same, but it feels cheaper, right? There's this feeling of like, oh, it's kind of nice to see 95 cents at the gallon at the pump. Let's see, what else? Why else would you want to go metric system? Because you weigh less, right? You're going to be a 59-pound woman instead of a 130-pound woman. Doesn't that? I mean, it's if you weigh the same, okay, yes, technically, but it kind of feels good to be like, hey, I weigh less. You can drive faster on the interstate, right? 100 kilometers per hour instead of 65 miles per hour. Isn't that great? Doesn't that sound fast? Exciting? I'm looking for creative ways to sell the metric system. What do you think? Is it going to work? Would you go for it? Less error in medical conversions. I know, but that's so boring, David, to save lives, convert to the metric system. That's not as exciting as going faster on the freeway, right? All right. Okay. Question 12. An extra strength aspirin contains 0.5 grams of aspirin. And we want to know how many grains is this? Grains. Grains is an old-timey kind of conversion factor that's used in the pharmacy. It's still used in some places today, actually. So we can calculate this. No, you're totally right, David. People don't care about saving lives. I mean, if there was one life, and they knew they could actually do something about it, they'd be excited. But if it's multiple lives and it seems like it's kind of a diffuse problem and it inconveniences them, then there's going to be some pushback, I think, like wearing masks, for instance. Anyways. All right. So, aspirin. First of all, step 1, what am I looking for? How many grains? That's what I'm looking for. Excellent. Number 2, what did they give me? Oh yes, grain did aspirin. We have 0.500 grams of aspirin. Yeah. And they also gave me that we've got every 1 grain of aspirin is 64.8 milligrams aspirin. This is definitely, oh my, not a metric unit. Okay. What else do we need? Anything? Yeah, we've got grams here and milligrams there. So we're going to need 1,000 milligrams of anything is 1 gram is what Erica wants to use. And that's true for aspirin too. Okay. Now we can set this up. I think we've got everything we need. So step 3. Where shall we start? Erica wants to start with 0.5 gram of aspirin. Okay, start there. Then what shall we do? David wants to do milligrams to grams, and he says milligrams need to be on top. All right, so 1,000 milligrams aspirin, over 1 gram of aspirin. All right. Grams of aspirin, cancel, and we're left with milligrams of aspirin. What shall we do next? Nicole says we're going to put 1 grain over 64.8 milligrams. Aspirin, 8 milligrams aspirin. Okay. And then our milligrams of aspirin cancels. And then David notes that we got what we're looking for, so we should stop and plug it in. So 0.5. Multiply that by 1,000, divide that by 64.8, and I should get 7.72 grains of aspirin. Any questions on that one? That one's pretty straightforward, I think. A little bit easier than the other ones we've been doing. Okay. As you'll notice, there's 25 questions on the practice exam, and now we're moving into periodic table. So you see the first half was on science and matter and math, and now the last half here is on atoms and elements in the periodic table. So number of protons in the nucleus of an atom is called what? Z, sure. Which is also the atomic number. Good. If I said number of protons and neutrons together, that would be the isotope number, right? Or the atomic mass, yeah. Okay, excellent. Atomic size of atoms changes in which of the following ways? Yeah, this top one. And I'm not sure that I remember talking about this one in the lecture last week, but it should have been in the lecture notes. This is a little bit, let me make sure that you guys understand why this is. We've got our little periodic table here. So as we go down in the periodic table, our shell gets bigger, right? We go from the 1s shell, the 2s shell, the 3s shell, it just gets bigger. And that makes sense because your mass is increasing. So your atomic size or your radius increases as you go down. But as I go across, I'm filling the same size shell. So it actually doesn't get bigger as I go across, even though I'm getting more protons and neutrons and electrons. Well, the protons and neutrons are in the nucleus. You can't see them. They don't take up really any space. And the electrons are occupying the same size shell. So they're not getting any bigger. But instead, what's happening is the electrons on the surface are more attracted to the protons in the nucleus because you have a larger positive charge in the nucleus. So they're held more tightly, and that's why it shrinks just a little bit going from left to the right. So this ends up being very large. On this side, it's relatively smaller because they are being held more tightly, the electrons are. Does that kind of make sense? It's a little counterintuitive to think that it would decrease going across because you are having more electrons, protons, and neutrons. But you need to know those electrons are in the same size cloud, which is then held more tightly. So that's why it goes down. Okay, number 15. Symbol for the element calcium is, all right, everybody got that. And remember, you have the periodic table and it has the names of the elements. So there's no excuse to not take 5 seconds and double check, okay? Even if you're like, I think it's calcium, I think it's Ca, just look, right? It's on there, it's right in front of you. Okay, imaginary element XQ consists of 2 isotopes having a mass of 100 and 102 atomic mass units. A sample of XQ is found to contain 20% of this isotope, the 100, and 80% of the 102 isotope, and we want to calculate the atomic weight. Oh, Nicole has got it. She's got that formula. Perfect. You're going to take that 0.2, which is the 20%, multiply that by the mass, which is the 100, add it to the 80%, that's 0.8, multiplied by the mass of that, which is 102. And when you do all of that, you get an average mass weighted for abundance of 101.6. Gorgeous. Well done. Some of the averages, but weighted for abundance. Okay. All right. Number 17. If an isotope has 110 neutrons and 68 electrons and a net charge of +6, then how many protons does it have? And everybody says 74. How do you know? David says, I take 68 and I add 6. What about the 110? This 110 is an intentional distraction. Just in case you didn't know what you're doing, you might be tempted to do something with it and then you'd get it wrong. Okay? It's useless because it contributes to the mass, but it doesn't contribute to the charge. But if you know these pieces, that is helpful because your charge is always going to be your protons minus your electrons is equal to the charge. That way, if you have more electrons than protons, then it'll be negative. If you have more protons than electrons, it'll be positive. So you just plug it in. So x minus 68 equals positive 6. And so 68 plus 6 gives you 74. Good work, guys. You were not tricked. All right, 18. How many protons, neutrons, electrons does this guy have? And I have to apologize about this one, but first let's answer the question. How many protons, neutrons, and electrons does this guy have? Okay, so just by the numbers, because it doesn't have a charge up here, it's got the same number of electrons as protons. So both of those should be 53. And then neutrons is just going to be 127 minus 53 gives you 74 neutrons. So we're looking for 53, 74, 53. By the numbers that are given, that would be the correct answer. Now, Alexander is completely right that the element xenon has 54 protons. So this is not the correct symbol for Xe. Like Xe should have a 54 here. But going by the numbers, we'll just go by the numbers. We're going to say 53, 74, 53, because there's nothing else here that's going to make sense, okay? Someday I'm going to go in and fix that, but for the moment, that's what we've got. Okay, does that make sense? Okay, number 19, which is not a general property of metals? Brittle. Perfect. Which of these characteristics correctly describes a proton? This first one, yeah. Mass of 1, charge of +1 in the nucleus. If I had asked instead, which of these is an electron, what would you say? Good. Tiba says mass of 0, charge of -1. So it's going to be this guy outside the nucleus. If I had asked which of these describes a neutron, what would you have said? Yeah, mass of 1, charge of 0, inside the nucleus, there's the neutron. Okay, good. All right, what happens if I add a proton to the nucleus of an atom? It makes it a different element. Yes. The number of protons is what defines individual elements. Good. Okay, which of the following elements has 4 valence electrons? Si, you just look at group 4 and you're done. Okay, that was pretty easy. Pretty straightforward. Did I miss anything? Any questions on any of these? I think we got them all. 25 points. I thought that meant there was 25 questions, but some of these are worth extra points. It's not perfectly weighted. All right, let's see how we did. 25 points. We got them all. Okay, that is it, guys.